Today I'll present the results obtained in the group of authors listed in the slides, and these results relate to the multi-layer representation of the higher order interactions in the collaboration network. You know that scientific collaborations can be listed in the form of collaboration networks, and these objects were studied previously, and there is a huge strand of literature devoted to this topic, but in most of these papers, authors considered simple graphs, complex networks, and they do not consider higher order interactions. However, it's evident that more accurate description of the collaboration process, scientific collaboration process, should include high order interactions, and so on. This process should be presented in the form of hypergraph. In these hypergraph nodes represent authors, and ages represent papers in which they are co-authored. We also can introduce dual object, dual hypergraph, where nodes represent papers and ages, hyperedges, represent papers. In this paper, we analyzed the multi-layer representation of these objects of hypergraph and primal hypergraph and dual hypergraph, and this multi-layer representation built in the following way. We start from the second layer. In this layer, we put only papers with no more than 2 authors. Then we go to the third layer, where we add papers with 3 authors. So we have papers with 2 authors and 3 authors, and so on. And the main question is, how many layers do we need to obtain proper description of the network? So it's natural to assume that different network properties should maturate when we go from layer to layer, as all we understand that papers with huge number of authors can't represent strong relationships. So the question is, how many layers do we need to obtain such proper description? So we analyze maturation of different topological characteristics, and today I will tell about the results. We analyze the publicly available data from the archive database. The general information about this database is on the slide, and we analyze not only the whole database, but we analyzed specific fields such as physics, math, and computer science. In this slide, you can see the small sketch, the small fraction of the hypergraph and the dual object, just to have correct description of the object. So figure A illustrates the primal hypergraph part, where nodes represent authors and hyperedges stand for papers. And the second, the B picture represents the dual object for the first one, where nodes are papers and the others represent hyperedges. Some words about annotations used. N stands for number of the authors. H is co-authorship primal hypergraph. H with star is dual quarter-shape hypergraph. G and G star is clique projections or pairwise approximation of H and H stars respectively. And we also introduce the notation H and small as a hypergraph obtained for n small level. So as a hypergraph or dual one or clique projection obtained with information only about the papers with no more than n small orders. And also n with bar is a maximal number of the maximal layer, maximal number of authors in the paper in the database for the respective field. So as the first characteristics of the considered hypergraphs, I would like to show the diagrams of cumulative distribution functions. Here we see that in physics, this distribution function can be divided into two parts. The first one, both parts can be described approximately by power law, but we suppose that these parts represent different activities for the field of physics. The first is for mostly for theoretical papers, and the tail is for experimental collaborative papers where a huge number of authors participate. And for maths and CS, we see that distributions deviate from power law only in tails. To introduce the notion of maturation, we should introduce some more notations. So let us say that xn stands for the value of some property, topological property on the level n in the clique projection of the hypergraph. We say that some property maturates on the level tilde n if its value deviates, starting from this level, its value deviates from the value on in the whole graph only no more than for some small number, epsilon number, and here we fixed this number on the level of 5%. Just to give you a short description of the general results which we obtained, I'll show some figures which describe the key ideas that the key results which we obtained, and after that I'll give more proper description about different characteristics. So the first figure A, demonstrate the dynamics of the average degree in math and computer science. Here, the shaded area demonstrates the 5% interval between from the final value in the whole graph. And here we can see that in math we see early maturation of the mean degree. However, in CS, this value does not maturate. Figure B demonstrates the case of diameter and characteristic path length in math and CS. And here we show that different topological measures may maturate at different layers, as you can see from this example. And the last figure, figure C, demonstrates the fact that that primal and dual graphs could be really different. For example, in the field of physics, for the mean degree, we see that in the dual graph we obtain rather early maturation, while in the primal one these characteristics doesn't maturate at all. So going to more proper description, I'd like to start from general properties, from maturation of number of nodes, ages, and component structure. So first of all, the first thing which should be noted is differentiation in the maximal layer in the statistics. So we see that in math and CS, this layer is much smaller than in physics and, of course, in the whole database. Moreover, in physics, we see that number of nodes maturates rather quite late, and this shows that in physics a consistent number of authors write papers only in huge, rather big collaborations. Then in math, we see that even number of ages maturate at the eighth level. So we can say that after level 8, we know about this graph everything. And the next notable feature is relatively early maturation of component structure, the size of largest component and the number of components for all of the fields maturates quite early. So we, on the early levels, we obtain the backbone of these graphs. And finally, we can see that in the dual graphs, all of the properties maturate relatively early. Therefore, these objects are better representations of the process in terms of maturation. Turning to degree distribution, we analyze mean degree and tail exponent for the degree distribution, and here we see that mean degree, as I already shown in the picture, maturates only for the field of math. However, in the dual graphs, for all of the fields, even mean degree maturates. Moreover, in dual graphs, we see that tail exponents of the degree distributions are higher than in the primal objects, and therefore we also can say that dual graph is better approximation, is more accurate description of the process. Then we are describing clustering properties, and here we analyze the values of global and local clustering coefficients, mean local clustering coefficients. So here we can say that global clustering coefficient maturates only in dual graphs. And speaking about mean local clustering coefficient in dual graphs, it maturates earlier than in the primal one. And turning to diameter and characteristic path lengths, we see that in physics, the value of characteristic path length is significantly smaller than in the field of math and CS, but this value doesn't maturate. So speaking about characteristic path length, here we see that in physics, large collaborations connect orders which weren't connected in the small groups. Then maturation indexes for diameter and mass are close to the values obtained for the number of nodes, and therefore we can say that in these fields, large collaborations mostly formed around people who already worked in smaller groups. And so the last point is already noted that in physics, large collaborative papers may influence the network's structure. And in this case, the dual graph is also mostly more reliable, as we already speak about. So turning to conclusions, the main results, the main conclusions obtained are in the fact that in different fields, different topological features can maturate at different fusion indices. And for example, for the fields such as mass and CS, we obtain earlier maturations of different topological properties. And moreover, we see that in terms of maturation, the dual representation is more stable, if you can see in such a way, or more reliable than the primal one. However, I think that one of the most interesting results is that the backbone of all the networks maturates quite early for all the fields. And so I think that here we can stop and turn to the questions.
Okay, thank you a lot, Ekaterina, for your really beautiful presentation. I'm sorry that you were interrupted by, technical issues. We have time for a short question from the audience, if there is any.
I think we haven't.
You don't have from there?
Yeah.
No. So again, thank you a lot, Ekaterina. Really, thank you a lot.